In this episode of the Back Engineering Show, I'd like to talk about a relatively turned popular technique called mutual TLS or MTLS. It's not something new per se, because it's been there since day one, I believe, but it's been popularized by specifically certain use cases related to microservices. And this is what I want to talk about. In order to talk about that, obviously, we need to talk about what TLS is, right? What is the current most, ubiquitous way of performing authentication in TLS. Then I'm gonna talk about like what kind of disadvantages is associated with that. Gonna talk about what MTLS is, what is the mutual TLS really is. Talk about the advantages, problems that it solves. And obviously, nothing is free in software engineering. You introduce something, it comes with its own sets of problems, and that's what we're going to talk about. We're going to talk about the disadvantages or things to watch out when you implement mutual TLS. Let's jump into it. Welcome to the Back in Engineering Show with your host Hussein Nasser, and this is our long-form, in-depth conversation about one topic. I like this podcast because this is the only time where I can take one topic and I go as deep as possible in that topic. You can't do that in 60 seconds or a few minutes. You need time to explore these options and talk in details, and I totally understand some of you are not fan of this long form content. You prefer short 8 to 10 minutes video, but some of you are like this kind of long form content, and this is, I guess, for those kind of people. So let's jump into it. So we start with discussing what TLS really is: transport layer security. It was invented to encrypt the communication between two parties, client and server. Right? They exchange symmetric keys using a key exchange algorithm. And once the same key exists in both machines, then they use that key to encrypt the communication. Any packet they send is encrypted first with that symmetric key, and as a result, no one in the middle can actually see the actual plain text, right? And even better, no one can modify it, right? Because if you did modify anything, that's the most, dangerous thing in the internet, that can lead to bad things. Because if you can go to a site and I change that to make you go to another site, that is very dangerous. And this used to happen all the time with plain text unencrypted HTTP. You see, if you go to http://google.com in the old days, a GET request will be sent, and that GET request will be translated to, the layer 4, which becomes a TCP segment. Before that, we establish the TCP connection. Once we have that in layer 5, the session file descriptors and all the session variables and session metrics, then we move to create a segment, and we ship that segment, that data you sent, into a segment. It depends on the MTU and the size of the segments and how large, based on the the protocol that we're gonna and based on the algorithm of slow start, how big that how many segments we can send also is controlled by something called the slow start algorithm and the congestion avoidance. And I talk about that in my networking fundamental course. It's right here. Check it out. Go to network.husseinnasser.com for a discount coupon. That link directs automatically to Udemy with that discount apply. So that GET request will be shoved into a segment, and that segment, let's assume for simplicity, it's just a single segment that will travel, right? It will be into an IP packet. It will go through the first, your router, my router is out there. That's the first destination. The router will start to do NATing, and it will send it across the internet, right? And the first thing that it will go through my ISP, right? So anything I send goes through my ISP. So my ISP is on path, It has to go to. It's my gateway to the internet, right? The autonomous system of my ISP, right, connects me to the wild internet, and there are other routers that control that. So the fact that everything I send goes through my ISP, that means my ISP sees everything I send, right? Except if it's encrypted. In this case, it's not, right? I'm sending in a plain text GET request going to Google. So if my ISP or any man in the middle that happened to be on my route, okay, sees my data, that means they can change it. So they can pose that IP packet, and instead of actually forwarding it like normal routers will do, they can respond back to me saying, hey, actually, here's where you're supposed to go. HTTP code 301, redirect to this website. Okay? And this website is owned by the attacker. So the fact that you went to google.com, you are redirected to a site that is not Google. And now you are completely in the control of the attacker. And that act of the redirection establishes another TCP connection and goes through that. And that new site could be encrypted. But the fact that we did not encrypt at the beginning is the problem, right? So what we do is we try to always encrypt the connection first. And that's what we use TLS for, which is awesome, right? So sending a plain text HTTP is just a bad idea in general, because this could happen, right? So we invented HTTPS. You always start with HTTPS. Let's always use TLS. Let's always encrypt first, right? So in this case, you establish a communication and everything is encrypted. But that's not what TLS is only used for. TLS actually is used for authentication. What does that mean? It means that if you're connected to google.com, right? How do you know that you actually hit google.com? TLS can guarantee that. You see, when you establish HTTPS connection, not HTTP, right? Pure HTTPS. You do the TCP connection with the server. Right? You got the server. And then you turn around and then you do a TLS. You send a TLS hello, which has this key exchange that we talked about, and says, okay, use this algorithm and use this key size and use this. And it has a bunch of parameters. And inside that, there's something called the SNI. There is an extension in the TLS called SNI, server name indication, that tells you that, hey, I want to go to google.com. But you might say, Hussein, didn't we just do a DNS? And I asked for the IP address of Google. Isn't that enough? Not really, for many reasons. Because once you get that IP address, you lost that knowledge that you're connected to Google. You're connected to a reverse proxy. And then you will send that SNI. And from that SNI, from that text that says, hey, I want to connect to google.com, in the extension, in the TLS, the server is responsible to serve you back what we call a certificate. Okay? So that certificate contains the name, google.com, because that's what you requested. Say, okay. And it contains something called a public key. And it can contain a signature. And that signature is signed by the private key corresponding to that public key. Why? Because that's the only way we can guarantee that we can ship back that certificate. And if you got the certificate, you can verify that this public key actually participate to this certificate. How? Well, you take that public key and you decrypt that signature. And if it verifies correctly, that means whoever signed this must have the private key. And now we know the certificate is valid. But that's not enough. Why? Because anyone literally can do that. You can create a public key and private key and claim to be facebook.com and create a certificate that is self-signed, right? That's not enough to verify that is accurate, because it will be. Right? So how do we prevent people from pretending to be Facebook, right? Servers pretending from being Google, right? What we do is we rely on a third party, on someone higher that can be trusted. And that's basically the certificate authority. So what Google and Facebook and any website does is, okay, here's my public key, right? You don't get my private key at all. Here's my public key certificate authority. You are trusted everywhere in the world. Please sign this for me, so whoever sees the certificate can trust this is my actual public key that belongs to Google. And certificate authorities usually do their due diligence to check that, okay, you are actually Google. I'm going to put a file in your machine. Let me try to access that file. Once that happens, okay, I trust you. I'm going to use my private IP address, my private key, right, to sign your public key. Okay? And this is a proof. And I'm going to include my public key as a certificate authority and my name and all the information, that you can see how large this can get. Now the question is, all right, I ship these two pieces of information to the client, and the client will take the certificate. I trust the certificate, but I don't trust this public keys belong to Google. Who signed this? Oh, here's part of it, says that the name is certificate authority. Let's encrypt. Oh, let me check my certificate store as a client. Oh, that looks good. The certificate authority is right there, is my store. Let's Encrypt is actually trusted. That's enough for me. I don't need to go any further in the chain. That's enough. Or that is not enough. Why? Because I could not find a Shark Encrypt certificate authority on my store. Is this really trusted? Who knows? Because maybe this certificate authority is just doesn't exist in my cert. I'm an IoT device and I don't have a large cert store. I have only basic things. Sure, okay. The chain that the user sent actually included who signed that certificate authority. And it could be another certificate authority. And that could be another certificate authority. Yeah? Up until we reach the certificate basically that doesn't have anything above it, the root certificate. And once we reach that must exist in the store. If it doesn't exist, the client rejects the certificate. And that's basically how the verification happens. So you can see that the chain, including the entire chain, could be expensive. And this is another topic that I'm going to talk about in another podcast, where these certificates are not actually compressed by default. You receive all these things from the server, and if you understand how networking works, these need to be placed into segments, and if they are too large and the MTU is too small, these need to be sent as multiple segments, right? And as a result, can delay the TLS handshake, right? Obviously, for 2 or 3 handshake, who cares? But if you're massive, your scale content delivery network, that adds up. All right, so that's the authentication part. So advantages of this, you notice that we only authenticated the server. The server sends us the certificate, and we never said anything about the client authenticating itself. That's how most of the internet works today. We ask to connect to a server, and the server sends us the certificate so we can verify and trust it. That's how most communication works. And it's very useful, because if I carried out as an attacker a DNS poisoning attack, what is that? I intercepted the DNS, which is mostly unencrypted until we get DOH or DOT mainstream. As an attacker, assuming I am en route, Starbucks and I did an R poisoning and I pretended to be the gateway and all the IP packets are now going my way instead of the actual router. So I am en route. I can see and change everything. So now if I see a DNS going to Google, I'm going to immediately answer the user. I'm not going to even bother sending that DNS request. So google.com is actually 1234, and 1234 IP address is actually run by the server, by the attacker. So now the next thing that the user will do is actually establish a TCP connection with 1234 instead of Google's IP address. Pretty cool, right? So now the TCP connection is established because it's just TCP has nothing to do with authentication. Hey, it's an IP address. I'm going to connect to it. And I just connected to the attacker server. Okay, it's not a big deal. We didn't exchange anything yet. Let's continue. The next thing, what do I do immediately after TCP? I do TLS, right? I send the TLS hello. And I say, hey, I want to connect to google.com again, right? So this is the second time we mention the host name. We actually mentioned it 3 times if it's HTTP. And the first in the DNS, the second in SNI, the third is the host name in the header, HTTP header. So I'm going to include in this SNI server name indication, right, as a plain text. There are efforts that try to encrypt that. ESNI, I think, failed, right? Encrypted client hello, encrypted client hello is trying to encrypt all the thing, and mostly succeeding, I think. I don't have much information about that, but you can dig deep into that. We might talk about it also in the future. So now I sent that. I say, hey, I want to go to google.com. I know where I'm going to go. I have that stored. I still need to go to google.com. All right. The attacker will receive that. The attacker will receive a request to establish a secure channel with itself, but it is the client's asking for google.com certificate. Do you think the attacker has that? They don't. The attacker does not have that. Right? The attacker can create easily a self-signed certificate claiming to be google.com. But the client will immediately reject that because it's self-signed. It won't find it in its certificate throw. And there is no certificate authority that will sign a certificate claiming to be Google that is not Google, right? Or Facebook or anyone. Right? Except DigiNotar, which happened like a few years back, maybe 10 years ago, where certificate authority, I think, got compromised and started signing certificates for Google and Gmail, and it was nuts. Right? Read more about it. Just type DigiNotar, D-I-G-I, Notar, N-O-T-A-R. So yeah, it's interesting, right? So that's why certificate authorities are very critical. It's like if you got compromised, you're done. So the attacker cannot do anything. So if the TLS session will be aborted and the client will be protected. That's why when you ever receive a bad certificate, the browser will give you this warning. Don't click. Someone tried to hack you. Blah, 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 blah. X, dude, don't do this. Don't enter the site. That's why it's bad, right? To accept bad certificates, right? All right. So we're protected. What's wrong with this? This seems perfect, right? Seems absolutely perfect. Until now, we're going to get to MTLs. What do you guys have? It's like, let's chill. This is a chill podcast, okay? Like, why is everyone in a hurry? Right? Like, okay, I tuned out after 1 minute. Boring. I know, I'm boring. But yeah, just like sometimes you need to chill, relax, Like, yeah, what do you have? You're just listening to this in the gym. Just relax and do more push-ups. Okay. Now, the problems with this as it's done today is, what if the attacker doesn't need to pretend to be at the server? Imagine this, Netflix. This has actually just happened to me. someone sent me a text from Netflix saying that your payment method has been declined on the same day that Netflix charges my account. And funny enough, I actually changed my payment method 2 months ago. So that was I almost believed it. It's like, oh, your payment has been declined. Click here to re-authenticate or whatever. I was like, oh, really? What? I thought it went through. I was like, you suckers. He tried to get me to click and give me my password. And it was a site called netflix.7za.69.nasty.3am.com. That was the site. I was like, sheesh, okay. Thank God. I know if I click, nothing will happen, until I actually put my password. But, I try to, as much as possible, not get scared because I understand, what is gonna happen. If I click, they gonna know my IP address. So I would rather do a VPN and then click, But I also need to make sure that if I click, no cookies will be sent, and I know now none will be, right? Because this site doesn't know me. I never visited it before. But still, to be sure, don't click on any links, right? But also try to understand why you're not clicking on any links. Does that make sense, guys? It's like I don't like to tell people like, oh, just don't click any links. I like to explain. Does that make sense? Like sometimes it's like, okay, oh, don't put your hands on the fire. Like, why? Because you're gonna get burned. It's like, okay, that makes sense, right? But oh, don't click because because they're gonna steal your account, right? I was like, yeah, but it's not as easy, but it is. Anyway, back to the topic. So assume I was tired that day. I was like, oh, okay, let me click, let me fix. All right, you click there and then put password, Netflix. Wait a minute, why did my Face ID didn't work? Never mind, maybe Apple doesn't, something's wrong. Let me put my password. Oh, and I just sent my username and password to the attacker, and the attacker got my credentials. What would the attacker do next? They will log in, to my site, to Netflix on my account. And Netflix, assume no two-factor authentication was enabled on my account, right? We'll let them in. Why? Because they have the password. But what happened about all this authentication, Hussein, that you're talking about? Well, the attacker, let's assume attackers from, I don't know, somewhere, right? Russia, Belarus, Australia, anyone from Australia, right? I love when I come to the US, it's like the S is pronounced sh. I don't know if you noticed in the Americans, like strawberry, Australian, I don't know. Maybe it's just, this is what I noticed, like American versus British. Random, very random, I know. But from Australia, we connect, the attacker to connect to Netflix, and Netflix trusts it, right? Because Netflix will send its certificate to the attacker and says, okay, you can access for sure. Enter your username and password. Boom, log in. It's like, yeah, oh, you're looking from Australia. What's happened? It's okay. I have relatives in the Australia and they have my password. And that's very common, right? People share their password. And so they will let you in, definitely. And someone just entered your account. That easy. Phishing attacks. Brute force. If I brute force it into a connection to a Postgres database, right? We see the news all the time. I try to brute force public Postgres or MongoDB or Elasticsearch. And then they guess the password, because it's not hard. And then they are in, even if the communication is encrypted, because the attacker has served the certificate of the server. And the server, will send that, and the client will authenticate. So say, yeah, I trust you, server. The attacker will say, yeah, I trust you, MongoDB server. Yeah, wink, wink. And it will let in. There is no other way of authentication by default. And this is part of the problem. So attackers can access this information and read and steal, right? Credential stuffing. They found your password somewhere else. You used the same password for your Bank of America and Pizza Hut, ordering from Pizza Hut, right? Password capital P at SSWRD1, and you use that, right? And then you logged into your Pizza Hut. You logged into Pizza Hut, and then someone leaked the database of Pizza Hut, and your password got exposed. Let's assume they didn't salt or do any fancy thing. It's right there, plain text. So yeah, they're gonna use that on your other accounts, and they're gonna log in. So this is called credential stuffing. And they can, because there is no other authentication. This Bank of America doesn't know it's you or not you. It just knows that someone tried to access. It's like, we let them in. They had the password, sure. Another problem that usually happen was API keys. How many times did we hear of someone pushing their token or API key in GitHub, publicly visible? That's nasty. I did it once, for sure. So if that happens, then someone can take that key and impersonate a client making a request to an API gateway. That's kind of nasty, right? So yeah, we have all sorts of problems with these things, with the original one-way authentication of TLS. Right? How long was that? Maybe 20 minutes. Now we're gonna discuss MTLs. I'm gonna put chapters. What is this? These chapter notes, guys. Don't worry. Right? So, how do I solve these problems? Okay. One more problem. Before we jump into that, I need to talk about microservices here. Microservices came into the picture as well. We have services, each service, let's assume it's in a container. So it has an IP address. So we have service A, service B, service C, service D. And all these services need to connect to an API gateway, but service F and G and X doesn't have any business connecting to this API gateway because it doesn't need to. So you might say, Hussein, just all these services are actually in the same network. Right? Why? Because it's easier to put them in the same network. There's no business. Even if they are not in the same network, they are in different subnets, but they still can communicate with each other. It's one network. Right? At the end of the day. So how do you prevent these services from connecting to the API gateway? Because they don't have any business connecting to this. Well, you can say, hey, hardcode the IP address, the individual IP address, into the firewall configuration and block any attempt. You can do that. You can put only the authentic things that can access the API gateway into a subnet, and anything that doesn't into another subnet. But that gets complicated as well, right? I guess. Yeah. You can do it. I'm not gonna say complicated. You can do, everything can be solved, right? But I can't imagine, it's like, okay, what if this needs to access and it's not in the subnet? You start adding more subnets and stuff like that. But maybe there is a better way, right? Through whitelisting. It's like, okay, here's who can access me, and here's who can authenticate with me, right? So this is another problem that can be solved with mutual TLS. Let's talk about that. So mutual TLS is not something new. It's been there since day one, since we released TLS, right? And the idea is, when we establish the TCP connection, followed by the TLS handshake, and then let me get up there. And then the server comes back, and the server will say, okay, here's my certificate. And by the way, I am configured as a backend to ask for your certificate. Otherwise, we can't complete this handshake. So here's a request for a client certificate. That's what mutual TLS is. It's just asking for client cert. Nothing fancier than that. If the client is providing the certificate and the server is providing the certificate, this is called a mutual TLS. That's the name is. So in this case, if the server requested the client certificate, then the client is forced to provide the certificate, right, to the server, right, after that step. And the server will receive the client certificate and will do exactly the same thing that the client did with this certificate of the server. It will do the chain. It will verify that the client identity, and maybe it's going to use the domain name. Maybe it's going to use something else, but it's going to verify it. It's going to use some sort of a cert store to verify against that. And only those that have been previously trusted before in the server will be allowed. The TLS handshake will be aborted if either the server certificate is rejected or the client certificate is rejected. So it's more secure. It's way more secure. Right? So now this becomes like, if you think about it, this is kind of problematic, right? Because we have way more clients than servers. That's why it's very hard to implement this in the internet. But we're going to come to that in the disadvantages section. So now, the beauty of this is, even if someone stole my password, or someone stole my API token, or API keys, or someone phished me and got my password, if they used my password or my API key against a server that supports mutual TLS, they won't be allowed inside because they need to present a client certificate that has my name in it. And my name, you can think of it, it's just another domain probably. And that will only allowed if the client is trusted. So that is extreme level of security. That's pretty good, right? Especially in a tight backend environment where you have control about all of this stuff, obviously, right? So we kind of solve this problem, right? That's pretty neat. Microservices, yeah. It's like, I support this kind of mutual TLS, and here are the domains that can connect to me. Here are the services that can connect to me. Service A, service B, service C, service D, and these are could be thought of host names or domains. Service D, and that's it. Right? If a new service was added and required an API gateway access, then you just basically give it access to that, right? Just add that to the cert store and make the server trust that new service. As I was editing the video, I also thought about this. It's very cool. If you can add that service, and any client that has that cert, no matter what network they live on, no matter what IP address they have, they can access. So that's an advantage of this. If you do it at the network level, if you block it at the network level, you would have to do this configuration at the network level. So it might get hairy if you implement it at that level, but it's better to implement it at the higher level. So another advantage for MTLS. Back to the video. Right? So that is obviously, all this requires management. It's not for free. Managing certificates is a team worth of effort. No one person can do it. And I think it's being tried to be automated, but obviously automating something is not enough. You need to understand how it works, because if it breaks, someone needs to fix it, right? That's why we do all this stuff. We try to understand. We try to get to the bottom of everything, and focus on try here. I'm trying to understand these things. I don't know everything, obviously. So it's very interesting. And I'm looking here because these are my notes. I have literally just 3 notes, just talking through this, not reading anything. But yeah, so with microservices, now a network engineer might say, you guys are just too lazy. I wouldn't even allow the TCP connection to be established. You can have further network level restriction, if you will. And I would have agreed with that network engineer. Right? It's kind of, we're putting, what is the saying, right? There's a saying here. We're throwing the baby with the bathwater. That's the closest thing I can think of. And it means like, hey, instead of, hey, we have this problem that I don't want this service to connect to this, right? It's like, okay, why don't you use networking? Oh, network is too much complicated. Nah, I don't want to. Right? I throw everything and I'm going to invent this mutual TLS thing to solve this, right? So it's like you throw everything and you create a new thing instead, right? Yeah, you can solve this problem. Like, okay, this service cannot access this by using network configurations. But again, I would imagine there is some limitations to why we reach this level. And I'm not aware of these limitations, right? Yeah. Because it's definitely cheaper performance-wise, and I'm not going to say infrastructure maintenance effort to prevent really just the connection at all. Just like block it right in. It's like, hey, this network, this subnet cannot access the API gateway subnet, and you can block it. You can put in its own, virtual network, so to speak, right? That's Amazon allows you to do that, I believe, right? So you can do all these tricks, but I believe there is always an exception, and these exceptions are the nastiest one. So maybe mutual TLS management is easier in that case, but I might be wrong there. So that gives us to actually the problems of mutual TLS. What's the disadvantages of mutual TLS? Like, sure, we always trusted the servers, but how much expensive it is to trust the clients, right? How much config do I need to do? How much management, how much maintenance do I have to do this client cert, to do this mutual TLS? I can't imagine anything that you need to extra do that definitely have extra cost, unless there is a way to somehow have this certificate managed cert store be centralized for both servers and client. And I think that might be it. Right? How costly is to manage this store? Updating that, reissuing certificate, right? All of that stuff. There's a cost to it. Sure, I guess you can argue that this is the cost of doing business, but it's a cost regardless. And I would leave it to the DevOps engineer who actually deals with this on day-to-day basis. Maybe you guys can tell your war stories or horror stories when it comes to managing certs. I don't know if it's hard or not. I never did this before. Another problem is we have way more clients than servers. So yeah, with servers, we have the certificate store, and we usually trust certificate authorities better, and anything that is signed by the certificate authority, that's enough, right? And if we trust the certificate authority, it should be enough, right? If you have one certificate authority, and as long as you have a certificate, that should be enough, right? Once we know that this certificate is signed by this certificate authority, and you manage to get a certificate out of the certificate authority, which makes me now think about another chain of attack where an attacker managed to spin up a container in the network and requested a certificate from the certificate authority. I would imagine, because now you need to prove. I mean, how do you prevent that? That in itself sounds like has to be done by some other, administrative almost process. Nobody can just request a certificate. Otherwise, anyone will just request a certificate and they're going to get it. So this is really, interesting to think about all this stuff. And another problem I can think of, even if you have mutual TLS, right? You have mutual TLS in all your microservices, and you have, A to X services have access to the API gateway, and only those guys can talk to this. Okay? And let's say your API gateway got pushed to GitHub or stolen, or whatever, session key got leaked, and you're an attacker, and you now want to use that API key. You might say you can't, because you're an attacker. You can't really just connect to that API gateway internally because you don't have access to it. One, then you don't have mutual TLS. But what if I talk to the reverse proxy, to the load balancer? It says, hey, load balancer, here's my API gateway. I'm outside the network. I'm completely outside. And I sent a request with a header, with an authentication header with my API gateway that I install. I don't believe we have mutual TLS by default with reverse proxies publicly, right? It's like anyone can connect to that public load balancer. So if we blindly take that request and forward it to an internal microservice, that microservice turns around and establishes a TLS session with the actual API gateway inside the microservices network. And at that point, it's trusted. So now it's almost like the attacker has been proxied by a trusted mutual TLS microservice. It's completely useless because the server will be authenticated, and you'll retrieve the result from the database and will be authenticated, and then get back the response. The load balancer will respond to the attacker and say, hey, here's your data that you requested. Cool. So mutual TLS is useless in this case, right? Because it's not all the way, exposed publicly, right? It's completely useless in this case. So you need to find a way to actually have a way to tag the key with certain either IP address or a domain, that's so that the load balancer or the reverse proxy can do a little bit, or the public API gateway, if you will, right? I keep saying API gateway is actually what's exposed to the public, right? While the authentication might happen in a downstream client, right? So yeah, these are some of the problems that I can think of mutual TLS. Obviously, nothing is perfect, but I try to always, when there's a new technology like this, and new in a sense like it's popularized, I try to think of what's gonna bite us later. I'm summarizing this. We're gonna end this show very soon. What can go wrong, really? Because we always, we are proud as a software engineer that when we invent something, we almost never talk about the possible disadvantages, right? You even see it in RFCs, right? Sometimes they talk about it. Sometimes, okay, we know about these current limitations. Sometimes, honestly, we just don't know. This is an honest thing. It's like, we just don't know. We just discovered these attacks as we go. Okay? I mean, even performance-wise and optimization enhancements, this happens gradually, right? It's like, why do you think we had HTTP 1.09 and then 1.0 and then 1.1, and then we enhanced this performance and we disabled the header compressions in 1.1 because we couldn't figure out how to solve crime. Crime, CRIME, capital, right? Forgot what it stands for. And then we invented HTTP 2, and we run into another problem. We invented HTTP 3 and Quick. And now Quick is perfect. everyone is talking perfect about Quick, best thing ever, right? And I'm sure a few years, if not so already there, people will find limitations in Quick. The limitation is to be 3 problems. I believe there are already problems because Quick is built on UDP. The statelessness of UDP is very scary, reply attacks, fragmentation, IP fragmentations, nasty things can happen like that. Protection at a higher level obviously exists, but it's always scary when things are stateless, right? Because anyone can just send it. There is no state persistent in the server like TCP, where hey, here's your sequences, here's where your window size. I know you can just send me something, right? I need to verify that it exists in my session, Yeah, and mutual TLS is no different. I think it's good. I think it's very good, but I think we should really pay attention to the limitations, and not just because something is, I guess, good doesn't mean we have to always implement it. Like, we can't implement a mutual TLS in the internet. Tough luck. It's like, what? Doesn't make any sense to be implemented in the whole internet, right? But certain services might. Like, I can see us in the future. Was my phone somewhere in my pocket? I think I can see something like a client certificate per phone or per device. Like my Mac, my phone would have a client cert, and I would register this client cert public key prior with Netflix, and it says, hey Netflix, you only these certificates can access you, right? These are my public keys, right? Or maybe I can create a domain and I sign this domain with Netflix, but then Netflix has to manage all these certs, which is something that they never did. Obviously they didn't have to, but maybe it's more secure, right? It's just, isn't this what passwordless is? I didn't read anything about passwordless authentication. Is this? Maybe it is, right? Because that looks like this might be the future, right? Passwordless, if this is what passwordless is, and not something completely different. Because, like, hey, I can register a certificate on the server, and mutual TLS is the future, right? Maybe, but good luck, like, having the server support mutual TLS and the certificate stores, and maybe it will happen, but I don't think it's impossible for certain big websites, right? It's definitely more convenient. It's like, oh, don't care about passwords anymore. Credentials, tokens, bye-bye. The moment you open your phone, if you have that physical thing with you, that's your key. That's your public key, and I trust you. And you have your private key, obviously secure. And obviously all of this should go to this, what do you call this? This chip. Keep forgetting this hardware stuff. Because it was bugging me, I had to Google it. TPM, Trusted Platform Module, which is a module that is completely isolated from the OS. It has its own memory, CPU, cache, and that module is responsible for storing and issuing private keys and all of that jazz. So Trusted Platform Module. So yeah, I would imagine the certs will, private parts, that's funny. The private sections of the certificates will go into the TPM. But yeah, all of this stuff is fascinating. And when I make these, these shows, I have a very general outline. And as I talk, I'm surprised by what I'm saying because I'm discovering new things. It's so funny because I don't have time anymore to sit down and just talk with kids and the life. But it's like when I do these videos, it's like I'm having a conversation with someone, and as I have a conversation, I'm discovering new things. And you'll be surprised, like I recorded this video like before, and I trashed it because as I was recording, I was thinking about all different things, and the videos like it's like, what is going on? It's like, you're all over the place. I am all over the place in this video too, but a little bit better. Hope you enjoyed this episode. I'm gonna see you in the next one. Again, you guys go to network.husseinnasser.com for a discount coupon on my network fundamentals for effective backend course, and check out my other courses as well. Head to husseinnasser.com. That is all the course. It supports the show, right? Consider becoming a member. Becoming a member supports the show. There is over 60 I think at this time it says 70 member only exclusive content. You get the slides for free, you get special badge, fancy stuff next to your name. You have special icons that you can use in comments and chat. Gonna see you in the next one. You guys stay awesome. Thank you so much.